All right, so we're back, and now we're going to talk about the tangent and cotangent function, but I want to answer a question that just came up while we were setting up this second segment. We had y equaled 100 cosine of 1/3 x, or x over 3, like this. Okay? And the transform form of this is this, like this. And Marty's question was regarding the old y and the new y. Well, this is what I call, and I've done this in a previous session, called the new function. The old function from which this originated is simply get rid of all the fancy stuff here. Get rid of the 100, forget the 3, and you've got a simple old function, y equals cosine x, which is in your library of elementary functions. Okay? So look at the math of what is being replaced. If you look at this pattern here, this old y right here is becoming this new y over 100. This old input on this elementary function is becoming this new input over 3. So the algebra on that is that your new y over 100 equals your old y. Over here, your old x is equal to your new x over 3. Look at the algebra. The new y, which is what you were interested in graphing, the new y values here is what you're trying to graph, are equal to 100 times the old y. That makes it 100 times as tall as it was in its elementary form. If you go over here, your new x is equal to, multiplying both sides by 3 times your old x. So you have grabbed a hold of your old function, this old elementary function, and you're multiplying all those x readings on the old thing by 3. And so you stretch that thing out by a multiple of 3. That's why it works. Okay. So, with that explanation, let's now talk about those other 4 trig functions. And right now in this segment, we're going to focus on the tangent and the cotangent. How do we think of the tangent? I'll just leave this up here for a second longer. How do we think of tangent? Slope of what? Oh, okay. There's a variety of ways. That's why I said, how do we think of tangent? So the tangent we think of in several ways. One way that we've mentioned, and people are remembering it, is we think of the slope of that terminal side when we use our unit circle. The slope of that terminal side when we use our unit circle in our standard angle measure, the slope. Another person said it's y over x. Now, it doesn't matter if it's a unit circle then. It could be any size right triangle, y over x. Okay. Is there another way? No, opposite over adjacent. Not adjacent. Okay, opposite over adjacent in a right triangle. Is there another way? I'm going to write all these up here in a second. Sine over cosine. Ah, there we go. Okay. Those are the ways I think of it. So if you had these notes about this previous little comments, I'm going to go ahead and erase that. So when we see tangent of x, we think of it as a variety of ways. We think of the slope of the standard angle, angle's terminal side. For instance, back on our unit circle, if we if we took a standard angle, say at 120 degrees, at 120 degrees on our unit circle, we know this is square root of 3 over 2, and we know this is negative 1/2. And that slope right there of that terminal side is negative square root of 3. If you take the y over the x. That's the other way of thinking of this, y over x. Y divided by this, multiply top and bottom of that fraction. I'll do it right here. This is called what kind of a fraction? Complex. It's called a complex fraction. The best way to clean up complex fractions is identify the common denominator of all the fractions in there, which happens to be a 2. And you multiply the numerator by 2 and the denominator by 2. And what you end up with, reducing out, the denominators inside there will always disappear if you use this approach. And you end up with negative square root of 3 on this example. And then opposite over adjacent works fine for acute angles, opposite over adjacent, but not if you go past 90 degrees. Opposite over adjacent. You have to think of it as y over x. Okay, so there's your tangent. The other way of thinking of it is if you were on your unit circle. Again, I'll use a sample angle like in the second quadrant here. We know that height right there is our sine of the angle, and we know that the x reading right down here is the cosine of the angle. And so again, y over x is sine over cosine of the angle. Sine of the angle divided by the cosine of the angle. That is the approach. That's what I want us to use to develop the graph of the tangent function. Think of it as the sine divided by the cosine of the angles. Okay? Any questions on this? Any questions? Should be okay with that, I hope, at this point. All right. There are several ways for me to help you develop or think your way into what the tangent graph looks like and how to remember it. The one way I want to start with is thinking of it as the sines values divided by the cosines values. I will show you another way related to the unit circle in a minute. Okay. So any questions on this? Because you have to understand this to be able to do what I'm going to do next. Everybody all right? Okay. I'm going to just erase this bottom stuff because what I want to do is I want to draw a nice light sketch, and we're going to lay the tangents graph on top of this. So what I want to do is I want to lightly draw a dotted sine wave, kind of large. Okay, that's clearly a cycle of the sine wave. And that barely shows up. I'm going to make it a little darker in segments so it shows up on the recording. Okay, so there's a sine function. Looks good. Now, I want to also lay a cosine graph on there too. And I think I'm going to do that with just a bunch of little circles. So we know a cosine graph using the same scaling here would lay on here like this, going through these circles I'm drawing. And then I need to have some more circles there so we can sort of see it. Right? So we have a cosine graph here of theta, and let me call it x, because books jump around. They use different variables here. we're familiar with using x, and now in trig we're using theta frequently. And then here's our sine function here, sine of x. Should feel very comfortable. Now, think about what we are doing when we want to develop the graph of the tangent of x, and we want to be thinking of the sine values divided by those cosine values. When I say values, I'm really meaning what on this picture? What do I mean by the values of the sine and the cosine on this picture? What do I mean by the values? Is it the x? If I was at the 30 degrees, if I was at 30 degrees here, what's the sine's value? Now the angle is pi over 6 or 30 degrees. The ratio is a half.
Yeah.
Right? At 30 degrees here, that sine graph is a half. Okay, when I'm at 30 degrees, the sine's graph is a half. That's what I mean by the values. It's the result of what the ratio value is coming out of this if you pick an angle. So it's the height that I'm seeing on this picture are the values. The heights that you see on this picture are the values. So look what's happening if we are between 0 and pi over 2 in this first region right here. Notice we're taking sine values which are growing towards 1, and we're dividing those by cosine readings which are dropping off towards 0. Look what happens if I want to spot check. Oh, and how do you typically build a graph the first time? When you have a function, how do you typically, the first time in life that you've seen this weird-looking new function, how do you typically build the graph? You plot some points, don't you? Don't you plot some points? So you probably would be building yourself a table of values. So if I pick values for x, like 0, and let's use radians just for the practice. 0 radians, so then I have the sine of 0 radians over the cosine of 0 radians. And the sine of 0 is, you have to have your unit circled. You have to be good with it. The sine of 0 is 0. The cosine of 0 is 1, and 0 divided by 1 is 0. So the tangent then, here's our tangent, isn't it? The tangent at 0 radians is 0. So I'm going to now use an x to indicate that I plotted a point. Let's go to pi over 2. I'm going to leave a little space in my table here. At pi over 2, I have the sine of pi over 2 divided by the cosine of pi over 2. And now I have sine of pi over 2, 1. We should be getting good at that. Cosine of pi over 2 is 0. How many times does 0 go into 1? Undefined. It blows up. That becomes undefined. How do you graph that on a picture, on a graph? You've done this in algebra. A what? A vertical asymptote. Remember those? Don't shake your head. Shake your head up and down. Okay. At 90 degrees, or pi over 2 radians, the tangent becomes undefined. You have to draw that on your sketch, usually with a vertical dotted line, and you have to label it. X equals pi over 2 is the location of a vertical asymptote, a trouble spot. A trouble spot. Look at this combination of graphing now, folks. You have a 0 here. We have an x-intercept right here for our tangent. And we have a vertical asymptote sitting here. What happens near vertical asymptotes on functions when you get close to them? What happens on the graphs, no matter where, if you're in algebra or now trigonometry? They either blow upward or they blow downward. Don't they? When you get next to a vertical asymptote up real close, okay? You start coming up close to it and it either blows up or blows down on you. Okay, and look at the values you're seeing for the sines and cosines in here. Aren't they both positive? Okay, so what's the graph have to do? It has to go up, like Elizabeth noted. Okay? It has to go up. Now, notice this spot right here, folks, where the cosine graph crosses the sine graph. The sine and cosine readings are the same, aren't they? If you divide one by the other, you get 1, don't you? You get 1. And notice that that is at exactly halfway between 0 and pi over 2. That's going to be at pi over 4. And does that make sense to you? At pi over 4, the tan...
the slope is 1?
Huh? Yeah. The tangent of pi over 4, tangent of pi over 4 is 1,
Yeah.
based on thinking of the slope of the standard angle's terminal side. See how this stuff ties together? Fits together like a glove. It better. Mathematics, if it doesn't fit together like a glove, you've got a problem. Okay? And there's always more than one way of seeing it. So the graph has to stay positive in this interval, doesn't it? And it has to blow up near that asymptote because you're taking positive values divided by positive values. And so there's a spot. Is it a straight line? No. It's probably going to curve. And what it ends up doing, and I'll just make it real dark, it's going to look like something like that. Reminds you of what from back in your algebra background? Kind of reminds you of one of the things I put up here earlier today. Well, the exponentials continue to go on out. Well, also, what I'm thinking of is x cubed. But it's kind of got that character, like an exponential, but it goes through 0. So it's kind of reminding me a little more of x cubed. But is it x cubed? Heck no. It's got a vertical asymptote there as a boundary. Now look over here. I want to make this a little quicker. Once you get past pi over 2 and head towards this location pi, so in this interval now between my fingers, notice what we're doing. We're taking positive readings here and dividing by negative readings. You see it? Positive values being divided by negative values. You have to end up with what kind of result? Don't you have to get negative values? Positives divided by negatives. Right? Positives divided by negatives. And so we have to end up with negative results. And now let's think about pi. What's the tangent of pi? Go back to your unit circle. When you're over at that angle pi, what's the slope of that terminal side? It's 0, isn't it? Right? So, or you can think of the sine of pi over the cosine of pi. I just don't want to take the time to write it. Sine of pi over the cosine of pi. Think of the unit circle, get both of those ratio values, and you'll end up with 0 over 1. Actually, 0 over negative 1. Because the cosine of pi is negative 1. And you get a result, though, of 0. So I'm going to draw it right here. So once again, we're going back to ground zero, just like you did when you started algebra and started developing the very first graphs you ever saw, probably y equals x. Okay? We plotted points, and we're developing the character of the graph. And so this graph has to be negative in this interval between pi over 2 and pi. And we're going to see behavior similar to what you see here, except it has to stay negative, so it's down in here like this. Now, what happens when I go past pi? Look at the picture. we have negative values for the sine divided by negative values for the cosine, so we're going to be getting negative over negatives are going to yield in this area right in here positive that results. And so what portion, or what are you going to expect to see? This stuff again. This stuff over here again. And that's exactly what happens, and we get trouble when we get to 3 pi over 2. Draw it, label it, and lay in the graph. We could go negative on our angles, couldn't we? Come back here to the left on our picture, come back to the left. And without belaboring it, I'm just going to go ahead and lay it on here for you. Looks like that, with an asymptote over here, and this is getting pretty messy. X equals minus pi over 2, another vertical asymptote. Okay. Do you see the period here? How much x does it take to finish a cycle and start repeating itself? 180 degrees or pi radians. You see it? You need this much, or you could start here and go this far. Make sense? We got this portion and we have that portion, and then it starts repeating its behavior once you get past that pi location. Or we could use the distance between the asymptotes. So the period of this thing, so here's what we've got. We have a function called tan x. It has a domain. The domain's going to be a little tougher because of those darn asymptotes. But the range, look at the range on that thing. How low can it go? Water level rising. Negative infinity coming up to positive infinity. Negative infinity to infinity on the range. And we have a period equal to pi. A range, we have a period, and now let's connect the thinking to the unit circle, where we were thinking of it as our, here's our angle, here's our sine reading, here's our cosine reading, and you can see that the rise over the run, the y here over, well, if I better use theta here. Y over x is the slope of that terminal side, and look at this, 0 at 0 degrees, going up in value. The slopes go up in value towards infinity as you move up through there, going through 45 degrees with a slope of 1, rising to infinity. That's this portion that we first started with right here. If you go right here, if you go past 90 degrees now, like with my eraser, if I have angles bigger than 90 degrees, then we can see that the slopes, all of a sudden they become largely negative, large negative slope here, rising up towards 0. From huge negative numbers coming up towards 0 in the slope. And that's this portion you see right here. If you go past 180 and start doing things like this, you're back to 0 again here, and these are positive, matching what you see over there in the first quadrant. Okay. People usually don't remember all those little details, but what do you need to remember? What do you need to remember? The basic character of the graph, similar to those things that you sounded like many of you forgot from algebra. What's a square root look like? What's an x squared look like? Everybody's good with that one, okay? Right? So you've got those fundamentals, hopefully, refresh yourself on those, and now in trigonometry, you need to make sure that you're feeling good about probably this is reasonable memory work for you. For your tangent graph. you remember from algebra again that might help you with this, even though it's different from algebra? Well, it's an odd function, but I mean, aside from that, it's similar, it has kind of that x cubed looking character, except x cubed has no bounds. It's not locked into asymptotes. It's x raised to the third power, so it just keeps on doing its thing as you move on across out to the right or out to the left, all real numbers in the domain, x cubed. This thing's locked in between these walls. Okay, so this is what you want to commit to memory as your elementary function. All right. Now, I could take another 10 or 15 minutes with you to do the cosine graph, but I'm not going to. We don't use the cotangent, I said cosine, I meant cotangent. We don't use the reciprocal functions near as much as we do these first three, sine, cosine, tangent. We use those all the time. The other three are simply reciprocals of the first three. So, to give you the cotangent graph, I could give you the same story. I could draw the cosine graph, and I could draw the sine graph, and this time I'm going to divide the cosine by the sine. Let's just go over here. I'm not going to do all that with you. I'm just going to give you the result. But the cotangent, I'm going to go ahead and switch back to using theta, is defined as cosine of theta over sine of theta, or it's oftentimes thought of as x over y. X over y. If you enjoy doing what I just did with you, with the dotted or the dashed and the circled sine and cosine sketches, it would not be a bad exercise for you to take yourself through that. But I'm not going to take the time to talk my way through it again with you. I just want to go ahead and give you the cotangent graph. What causes trouble in a fractional function? Where do you have trouble in the domain with a fractional function? When the denominator goes to 0 on you. Okay, this is something that you can remember that's helpful. You know that you have trouble with a fractional function if the denominator takes on a 0 value, because you're dividing by 0. You got trouble. Okay, so all you have to do is look at this overlay and observe where the sign is 0. Happens to occur here and back here at these zeros of your sine function. Those become what on the cotangent graph? Vertical asymptotes. Great. So here they are. Theta equals 0. Theta equals pi. Theta equals 2 pi. Watch how quick this can be. Positives divided by positives stay positive, don't they? So what we're going to get is we're going to get a graph that's going to stay positive, except it's going to be coming down off the asymptote here, near the asymptote, coming down, goes through 0 when the cosine becomes 0. Right where my eraser is, and I'm pointing up here in the numerator as well. And then in the next interval, from pi over 2 to pi, you have positive values divided, or negative values divided by positive values. You have negative results. And so this shape of the graph is identical, isn't it, to the tangent? If you think of the pattern behavior, the shape is identical, except it kind of looks like it's been flipped upside down or turned around, doesn't it? Okay? And we'll look at that connection soon. Finally, we could then play the game some more over here, and we could draw more of this, looking something like that. So to make a long story short, I'm running out of time on this segment, is this particular cotangent graph has a range, again, of all real numbers. You can see it. from minus infinity down low, rising up. And it's got a period of what? Pi again for your cotangent function. Could we apply transforms to these two new functions, tangent and cotangent, just like we did with sine and cosine earlier? Right on. Sure, we could. So we can stretch and squeeze these things and we can flip them around. We'll practice that later. Okay, let's go ahead and end this segment, and then we'll have a short segment to try to wrap this up. I can never get through 4 segments in a session, I guess, but okay. No, it's not due tomorrow. It's due sometime next week. So, but there is a homework quiz that's due, I think, tomorrow. Yeah, tomorrow by 5, I believe. Yeah. So don't forget that. Take a look on MathXL for that second homework, week 2's homework quiz. Okay. So let's wrap things up today with this short segment here on the last 2 trig functions we want to get under our belt is the secant and the cosecant functions. And you're going to like this. It's going to be very simple and straightforward. If you know your sine and cosine. So let's start. Let's just stay in the same order. What I'm interested in working up is the secant of theta's graph. Now, it is the reciprocal of cosine. It's the reciprocal of the cosine function. Reciprocal of the cosine function. So that's 1 over the cosine values. It's not an inverse. It's simply a reciprocal. So you take your cosine readings and you you take 1 and you divide them by your cosine readings. So in 10 seconds, I can tell you how to remember what the secant graph looks like. It simply rides on the cosine graph. It goes for a ride on the cosine graph. And now I can give you more details about that in a moment. But let me lightly dot in a cosine graph through more than one cycle. Okay? So here's a cosine graph through more than one cycle, through 2 cycles. From minus 2 pi to 2 pi. What I mean by riding on, look at this. Cosine, you get trouble in this fraction, don't you? If you divide by 0. So places where the cosine becomes 0, we have trouble. Again, similarly to what we just saw with tan and cotan, we're going to end up with vertical asymptotes at the zeros on that cosine function. So when theta equals pi over 2, we've got a vertical asymptote and then also over here at 3 pi over 2. Notice how you always see me use dotted lines on them, and you always see me somewhere off the graph label the equation of that. Now, what I mean by it rides on the cosine graph is it does the following. What's the reciprocal of 1? Still 1, isn't it? And if you start taking reciprocals of numbers less than 1, like a half, what's the reciprocal of a half? 2. What's the reciprocal of a third? 3. What's the reciprocal of 100? I'm sorry, the other way around. 100th. 100th reciprocal is 100. So what this graph does is it does this. This is what I mean by it rides on the cosine graph. Over here, we're taking reciprocals of negative numbers. The reciprocal of -1 stays -1, doesn't it? 1 over -1? Mm-hmm. And reciprocals of those others have to stay negative, don't they? Of these other negative numbers you see here. And so it takes a dive like this. There it is. Have we finished a cycle? Let's see. Let's go over here. What happens over here? Reciprocal of 1 is 1. These are positives. Reciprocals of positives stay positive. And these are numbers smaller than 1, like a half, a third, a tenth. Reciprocals of those become bigger than 1. And so the graph looks like this. Then what happens after 2 pi? Where does it go? Back up, doesn't it? Okay, so do you see that it looks like the behavior starts repeating itself right there? Okay. And so there's a period. There's a period. If I wanted to come back and draw some other regions of this thing, I could come back over here and lay these in as well. Okay? Notice that the cosine function you know is even. Look at the reciprocal. What do you think? The cosine function you know is even. Here it sits. Look at the reciprocal. Y-axis symmetry. Even. Happens to be even. We'll talk more about that later. So anyway, there's the cycle. The period is 2 pi on this thing. Same as the period of your cosine and sine. So in 30 seconds, we can end this. One last quick sketch. What about the cosecant graph? Rides on sine wave. Rides on sine. So you mentally think of a sine's graph doing its thing, right? And simply lay it on there like this. Now I can give you a more sophisticated explanation of that later, but all you have to do is remember that, and that'll help you immensely as you move further along in math and science. Again, the period of this one is 2 pi, just like the other. Last quick comment, just in the interest of time. It'd be nice if we could spend all day playing with this, and then I'd really wear you out, okay? We have 6 trig functions, don't we? 4 of them, 4 of the 6 have periods of 2 pi. The other 2 have periods of pi, which are your tangent and its reciprocal cotangent. Can you remember that? Okay. 4 of the 6 periods of 2 pi. The other 2 tan and cotan periods of pi. Okay, see you in here tomorrow. That's it. No fourth segment today. If you did not take